Welcome everyone to Acreon's tutorial series, From Dynamics to Feedback with Uncertainty. In this section, I'm covering the Cartpole's equations of motion, deriving them from scratch using Euler-Lagrange equations of motion. Okay, so today I'm going to be walking through the Cartpole example as described by Gymnasium's point of view or usage, which is a Python package used for classical control, LQR, and then it's starting to span like reinforcement learning and things like that. Um, the However, I'm going to describe it using first principles, Euler-Lagrange equations of motion, linearizing a point about the vertical, getting a state space representation, and then walking through the linear quadratic regulator, and then state feedback, state for observers, and then moving forward to robust controller techniques and things like that. So it makes it a little easier to understand how to do nice MIMO controls for underactuated systems without sending it all through a reinforcement learning package or you know learning the state space with neural networks, which I think there's advantages to that, but I want to try to bake things in so it's as transparent as possible because some of this material is a little bit more tricky to get around. So all that being said, let's break this down. So the cart pole is described as a cart that has a center of mass and it's a rigid body. And then the Python package describes the pendulum as a point mass. So there's no inertia. It's literally just a particle rigidly attached to the cart. We're going to describe that length as L. And for convenience, I'm going to describe a vertical about the center of mass of the cart to which the pendulum is rigidly attached. And then the angle here is theta. So that angle of displacement of the vertical with the point mass that describes the pendulum is theta. And then it's also given that the other generalized coordinate here is just x. And it can be pretty easily seen here that it is moving laterally in an I hat coordinate frame. However, let's dive into this a little bit more. So it's just a little bit more clear. I think generalized coordinates get a little hairy once systems become more complicated, and this is just a nice canonical example to walk through. So what I attach is a inertial frame X and Y here. The number of degrees of freedom can be described as 6 times the number of rigid bodies plus 3 times the number of particles minus C, and those are the number of constraints we have on the system. So we know we have one rigid body and we have one particle, and currently, I guess, an unknown amount of constraints. So the rigid body, though, can be described in X, Y, Z, and then we have roll, pitch, yaw. However, we can see here that excluding, I already marked the X on the lateral, but there's no motion about Y, there's no motion about Z, there's no roll about X, there's no pitch about what would be Z into the page, and there's no yaw about Y. So it's pretty easy to see that this is indeed the generalized coordinate here that can describe the cart position. And then now for the pendulum here, that's a point mass X, Y, Z. In an initial glance, it seems like how do we get from X, Y, Z to a theta? And it's really not too tricky. We can basically express it in polar coordinates. So we have a R and a theta, and then what would be R hat and theta hat unit vector directions. And then noting that our R here, or L, isn't changing, only theta is changing. So we pluck out the theta here, and we can essentially move from polar to Cartesian coordinates via just a homogeneous transformation with cosines and thetas, or cosines and sines. And so it's not too tricky to move between the two. All right, so that basically gives us the two generalized coordinates that we're going to be using. And so describing the equations of motion, I'm going to use Lagrange's equations. And so that's the kinetic energy minus the potential energy. And so the kinetic energy, we have the cart and we have the pendulum. And then the potential energy, we have, again, the cart and the pendulum. Now, the cart here, though, is 0 because mg is balanced out by a normal force pushing up on it. And so there's really no potential energy on the cart. We're kind of neglecting any kind of like roughness or anything there that could displace the cart. Um, Likewise, the pendulum, though, will have some potential energy associated with it because we do have that, potential difference there described by the theta. To start, though, let's dive into the kinetic energy of the cart. That's the most simple. So the kinetic energy of the cart, I'm going to start with describing the position of the cart is x projected along I hat, and then r dot c is just going to be x dot, and I hat doesn't change. So t cart, using the basic equation here, mc x dot squared. So that is the kinetic energy of the cart. Pretty simple. The next one, the pendulum, is a little bit more tricky because we have motions of the cart and the pendulum that we need to account for. And so what I'm going to do here is pick a different color, and then I'm going to go to this kind of like nice white space over here. And we're going to do this triangle here with the theta. We know that this is our r hat here. And then to get into I hat and then j hat components, I kind of like writing unit vectors that come out of the triangle. And so we can essentially pluck out the individual components from this theta hat and L that we know that's projected along R. So let's start breaking this down. So this would be RP, this is describing the position of the pendulum, is X I hat, and that's describing the cart position. I'm just going to get rid of the C because it's getting confusing. And then what we can say here is the I hat direction is going to be the opposite over the hypotenuse. So that's going to be a sine theta. So what we're going to have is L, that L component, sine theta I hat. And then for the j hat, we're going to have L cosine theta j hat. So then the time derivative of RP now is x dot I hat plus, and remember I hat's not changing, L is not changing, sine does change. We have a chain rule here. So theta dot cosine theta I hat doesn't change. And then actually this is going to be a minus, so minus L. And then we're going to have a theta dot sine theta j hat. So that's describing the velocity of the pendulum now. And so in a similar way, because we're just dealing with a point mass, we don't have any inertial components. So the T pendulum is going to be 1/2 and then MP. And then this is going to be our RP dot. So we have X plus L theta dot cosine theta squared. And then we have, this would be minus L theta dot sine theta squared. And then we can simplify this down a little bit more. So this will be, bump. So we're going to have x squared, and then we have a 2L theta dot cosine theta, and then we have L squared theta dot squared cosine squared theta. And this is L squared theta dot squared sine theta. You should already kind of notice a trig identity with these two that could be reduced. And so 1/2 MP x squared, sorry, I'm being a little lazy, x dot squared. And then we have 2L theta dot cosine theta, and then L squared theta dot squared. That's just one. And that is the kinetic energy of the pendulum. Okay, so I actually did mess up this squared term, the first one. I forgot to cross the x dot, so we're going to have a 2L x dot here plus 2L x dot here. So it's always good to just double check on these equations too, because it's easy to goof up. Okay, so we have our kinetic energy here with the pendulum. And now we need to describe the potential energy of the pendulum. The potential energy of the cart is 0. So let's use purple. And it can be a little tricky to start with understanding how, man, I can't even draw a straight line. Potential energy works with just various systems. But let's try to break it down and make it a little bit more simple. So this is our RP pendulum up at the upright position, which we're defining as a steady state position, which we'll use for linearization later on. And we know this is a delta height here, which is positive. So once we swing out, we're going to lose potential energy with a theta. So that's obviously can be either like a positive or a minus theta here. And so canonically, mg, delta h is the potential energy. But as we have the pendulum defined in r hat, and we have these, I hat, j hat unit vectors to help describe the pendulum position, we can see that here L cosine theta will actually sufficiently describe our potential energy in the j hat direction at the upright position. Now, if we had it defined at the bottom, we would want a shift term because for a theta 0, that would be minimal potential energy. So we would need to subtract that out by an L. But in this case, this would actually be the maximal. So L cosine theta with theta is equal to 0 implies L. Okay, so that being said, our potential energy for the pendulum is mPGL cosine theta. All right, so now we need to combine the kinetic and the potential energies together. So we have TC plus TP minus the potential of the pendulum. So this can be seen as 1/2 mass of the cart x dot squared, and then 1/2 mass of the pendulum. I'm going to put this into brackets again. We have x dot squared plus 2L x dot theta dot cosine theta plus L squared theta dot squared. And then we subtract out MPL, GL cosine theta. And this is our full Lagrangian. So I'm just going to pause here for a moment before stepping into Euler-Lagrange's equations of motion, which we seek to find for the x and the theta. All right, I took a quick break, but now it's time to jump into Euler-Lagrange's equations of motion. So the first one, let's back up for a moment. So the general form is ddt of the partial of the Lagrangian with respect to the generalized coordinates velocity subtracted by the partial of L, our Lagrangian, with respect to our generalized coordinate I. That's equal to Q NCI, which is our non-conservative generalized force in the ith direction. Where this comes from is the D'Alembert's principle of virtual work. Sorry if I mispronounced D'Alembert. But essentially what this says is the delta of the work non-conservative is equal to the sum of the forces acting on the non-conservative forces Fi acting in the direction of the virtual displacement Ri. And you can see from various texts or whatever to see that this is equivalently Q J dot delta QJ. So that's the non-conservative generalized force acting on our generalized coordinate J. And so QJ is equal to the sum of the FIs dotted in the direction of the partial RI with respect to QJ. Okay. So now this is kind of a fancy way. This is solely acting in the X direction here. I didn't write it down, but that would be our forcing function. It's solely acting in X. So there's no actual component spanning the theta direction at all. So this actually just boils down into this. So Fi dot delta X. So, and then for the theta, that would be 0. So now looking at the first equation with respect to X, we have ddt partial L partial Q I dot minus partial L partial Q I is equal to F. Okay. Oops. X dot X. All right. So now let's break this down. So the first guy here, I'll just use a different pen. So partial L partial X dot. That's going to be, we have MCX dot, we have MPX dot, and then we have 2L theta dot cosine theta. When we do dt of the above, we will have MCX double dot plus MPX double dot plus 2L. Now we're going to have a product rule here. So starting with the theta double dot cosine theta minus theta dot, and then this is going to be squared sine theta. Since that's changing with respect to time, and we have a chain rule on the cosine theta and the theta dot. So we can combine like terms. We can see that this is like our Newtonian F is equal to ma, our acceleration term here, 2L theta double dot cosine theta minus theta dot squared sine theta. Okay, and then this last term that's hanging out here, this partial L with respect to X, we don't have any X. So that term is actually 0. So our full equation here for the first one is X double dot MC plus MP plus 2L Did I forget yeah, shoot, I did. Sorry. So this is 2, and then this is MP. I forgot to carry the MP through. And this is 2 MPL. And then this is 2 MPL. There we are. Okay, so 2 MPL theta double dot cosine theta minus theta dot squared sine theta is all equal to F. So that's kind of like our F is equal to MA. All right, so next is our generalized coordinate theta. So we have the equation of motion in x direction. Now we're doing it in the theta direction. Dot minus partial L is equal to 0. Okay, so similar form here. Let's go partial L, partial theta dot. Let's look up above. We have the MP L x dot cosine theta, PL x dot cosine theta, and then MP L squared theta dot. The 2 drops, we get that cleanly. dt of the above, we're going to see a product rule again here. So x double dot cosine theta, then minus x dot theta dot sine theta with the chain rule. And then on this part, MPL squared theta double dot. Now we do have a theta component with on the Lagrangian. So here and here. So let's look at the first one. So we have DL, D theta. And so this first guy, MPL, and then it's X dot theta dot. We're taking this isn't with respect to time, it's only the partial of theta. So this is going to be sine theta minus. All right. And then we have cosine, so MPGL. It's going to be plus, so MPGL sine theta. Again, these are partials. It's not the time derivative of the cosines. And I think that is good there. So combining this whole term, we will have MPL x double dot cosine theta minus x dot theta dot sine dot, sine theta plus MPL squared theta double dot minus MPL x dot theta dot sine theta plus MPGL sine theta. Let's see, this is all equal to 0. So MPL x dot theta dot sine theta, MPL x dot sine dot theta dot, these drop, or these can be combined rather. So we have MPL x double dot cosine theta, and then minus, oh, sorry. This, we need to sum. That's why they can drop. Yeah. All right. So that's a partial L, partial theta, but combining, this is a plus, and this will be a minus. There we are. So then this can drop. That's what I was thinking. Okay, we have x double dot cosine theta here. Okay, MPL squared theta double dot. That stays. And then minus MPGL sine theta. If we can then do MPL x double dot cosine theta, and we have plus L theta double dot, and we have minus G sine theta equal to 0. And so finally, we have x double dot cosine theta plus L theta double dot minus G sine theta is equal to 0. And that is the equation of motion for theta. So we have our equation of motion for x, our equation of motion for theta. We have the forcing function F acting in the x direction. So, and we also have the notion of our steady state, which will be the upright position to which we want to linearize. And I'm going to take a break here. And what we're going to do next is essentially package this into a manipulator equation, linearize it about the upright position, and we'll have a state space form to which we can then perform control on.